All right, ladies and gentlemen, welcome back to the ME490 Senior Design Seminar Series. I hope you're all out there enjoying your first week, being happy and healthy, and enjoying your first couple of weeks here. It looks like someone raised their hand. Did someone raise their hand? Oh, I think they withdrew their question. Okay, today I want to make a few announcements, and then I'm going to play a pre-recorded video of Dr. Slaybach describing the design process. So the seminar today will be from Dr. Slaybach, who's in the ME department. I'm sure maybe some of you had him for a class. And he's going to sort of describe to you the design process. And the slides for his presentation are available in sort of the Teams folder for our particular team if you want to sort of follow along with his particular slides. And I would like you to pay particular attention to when he talks about the problem statement and what belongs in the problem statement. So one of my announcements for this week is that your problem statement will be due to me and to your advisor next Tuesday by 2 p.m. You'll email it to me, and then how you deliver it to your advisor, I guess, will be up to them. And I've provided a document in the Teams directory that also sort of details what I think are some good and bad problem statements, and maybe you can sort of look at those and understand why those might be good and why those might be bad. I think there's a little bit of opinion on what makes a good or a bad problem statement, but in my opinion, it should be rather concise and just specifically stating the problem. You don't want your problem solution to include, let's say, alleviations to the possible solutions. All right, so you just want to state what is the problem. This is the problem. Don't allude to possible solutions in your problem statement. That sort of comes later with the design process. Okay, so this is an important step. It's the kind of the foundation upon which all of your design is going to be built. So really consider your project, your problem statement, and maybe go over it with your advisors and make sure that's nice and clean. Okay. One other announcement is that based on conversations we had last week with Julie Way from Career Services, today is the day for you to begin scheduling appointments with companies that might come to the career fair. So I uploaded some documents as well that Julie sort of provided to us that might help you with some of the career services things that we talked about last time, like when is the career fair, who's coming to the career fair, how do I do my scheduling, what apps do I need to download, all those sorts of things. You guys and your fancy apps, okay? That's all the announcements I really have. Dr. Slaybach's video only goes about 25 or so minutes, so I'm just going to play that in the Teams meeting here. There's also a YouTube link to that video if you need to watch it later for whatever reason, and I will post that in the chat after I start the video. But without further ado, I think I'll just share my screen here and share Brian's video and play it through this medium, and hope that you enjoy it and pay close attention to his sort of laying out of the design process.
The design process overview. For those of you who don't know me, hi everybody, welcome to Senior Design. This will be one of your Senior Design seminars. We're going to be talking about the design process overview. For those of you who don't know me, my name is Brian Slaybach, and I'm in my second year here at MSOE. And for those of you I had in class or know from last year, I hope you guys had a great year and hope you have a really successful senior year. Let me just give you a little bit more information about my background so you can kind of see where I'm coming from in giving this presentation. I started my academic career, you can see, in 2015 at a place called Middle Tennessee State University, and the way that they did senior design is a little bit different than we do here. At Middle Tennessee State University, I mentored all the senior design projects, not like here where we have different faculty mentoring different projects. So I got to mentor about 40 plus senior projects in a very short time frame. So learned a lot from doing that. So let me show you some of those examples of senior design projects. We had walking robots. We had robots that made peanut butter and jelly, that played Yahtzee, that delivered your mail for you autonomously, made pancakes. A lot of really interesting projects that were a lot of fun. And so when I'm giving this talk about the design process overview, it's from the perspective of having seen a lot of teams go through this process and really figuring out what works for teams and kind of what doesn't. And so I just put together a list of what do successful teams do in senior design. Well, couple things. First, there's a clear project manager and technical lead. So you need to have somebody that, from a technical standpoint, is going to be making the final decision when it gets to the point where you guys have conflict about something. Somebody has to make the call. And you also need somebody, a project manager, that's going to keep the team on task, make sure you're hitting the deadlines that you need to hit. Another thing that you want to try to do is have each person work in an area of strength. Okay, great teams are built by taking everybody's strength and magnifying that, not taking everybody's weakness and having working on that. Now, I know that everybody's going to want to learn new things in senior design, and you can certainly do that. And so what I suggest is that each team assigns, you know, multiple people to one major area, whether that's mechanical design, electrical programming, controls, hydraulics, pneumatics, whatever it may be. You have a lead in that area, and then you have somebody that is a secondary lead, so that there's not just one person that is 100% in charge of something. You have maybe two people working on it, and so you take lead on whatever area of strength you have. Maybe you're a great programmer, so you take the lead on that, but maybe you also want to learn more about mechanical design, and so maybe you're secondary on that. All right. Your team's also going to want to have a process for dealing with conflict, because right now, early in the year, there's probably not much conflict, but I've seen teams get to the point where they're ready to throw punches. So you don't want to get to that point. You want to make sure that you have a clear process for dealing with conflict. And you also want to have a process for making technical decisions. Okay, how are you going to go about making these important technical decisions? And we'll talk more about some of those things later on in this talk. And another thing I've noticed that really helps a team is if you engage in some kind of non-engineering activity early in the term. You know, typically that might be going out to a restaurant or doing something like that. But you know, with COVID, you guys have to be creative. Maybe some kind of virtual activity. But you know, just connecting with your team away from the actual engineering project is a really good idea if you haven't done so already. And then you're going to want to have excellent documentation and very good communication skills. So let's talk about what the design process is all about. Okay, the first thing you're going to want to look at is clearly defining the problem. And this is one of the most important parts of the task. Okay, so the formal definition is that this is a phase in the design process in which customer and company requirements are determined and engineering design specifications are prepared. So here's the way you do this. First, you want to clearly define the problem at hand in your own words. All right, that's important. And the problem statement should be solution independent. And design problems are often ill-defined, and so the team should work with the customer for clarity. So you might be working with a company, and they may not have fully defined the problem for you. So you're going to have to work with them to make sure that the problem that you're trying to solve is clearly understood. So if everyone on your team cannot understand the problem, then there's no way you're going to be able to solve it. That is absolutely the first step that's important. So let's take a look at an example. So what you see here is a former robot developed by seniors at Middle Tennessee State University, and it's a robot that can sort Skittles. So let's look at which problem statement would be the most helpful. Okay, the first one is A. The problem statement is a 2 degree of freedom belt-driven robot must be designed to sort Skittles by color. Or B. A system must be designed to sort Skittles by color. Or C. An autonomous Skittle sorting machine should be designed which sorts Skittles by color, costs less than $1,000, fits into a 2x2 area, provides an easy to use GUI, and is safe to maintain and operate. All right, and these are just problem statements in your own words. Which of those do you think would be the clearest for this problem? And I think y'all would probably say it's C. All right. And one thing to notice about this is that this is not it's not specifying a solution. It's not saying that you need to have, 2 degrees of or 2 motors on a linear rail. There's nothing about the actual design solution. So you want to stay away from anything that would specify a solution. It should just be how should the product function? What should it be doing? And what is that problem that you're trying to solve? The next thing you want to look at is coming up with the functional requirements that needs to be identified to specify what the product should do. And so a way you can do that is identify certain sub functions of whatever it is that you're designing and how important each of those functional requirements are to the overall design. So for instance, you might be designing a bicycle. So let's look at different sub functions of that. So a bicycle needs to transport riders. It needs to, you need to be able to steer the bike. You need to be able to support riders comfortably. You need to be able to absorb road shocks. And there could be more than that. This is just a simple example. So you might say, okay, how important is transporting riders? Well, it's pretty important. So we'll say that's 50%. What about steering? Well, that's also critical. So maybe that's 25%. And you do this, and so that you can kind of get an idea of what things are really important in terms of function. So does the bike absorb road shocks? That's really nice, but at the end of the day, if you need a bike to get from point A to point B and it doesn't perfectly absorb road shocks, that's not the end of the world. So you give that a lower rating. And supporting riders comfortably, wow, that's nice, maybe not the most critical task. So you can see just by doing this and going through this process, you can see, oh yeah, transporting riders, you better get that right. Steering the bike, you better get that right. That's 75% of your design. The rest are nice to haves, but maybe not necessary. Now, what I typically do is if we were in the classroom, I'd have you guys all get together with your teams and actually go through the process of doing this for your project, all right, as well as writing the problem statement. So those are two things that I would suggest you do as a team. Write down the problem statement in your own words and maybe have everyone on the team do that independently and then compare and make sure that you all think you're solving the same problem. And then once you've done that, you can go ahead and do the functional requirements. What are the functional requirements for your project? And write those out and put down a weighting. Now, these weightings don't have to be perfect. This is more of just a way to get you to really think about what it is that you're trying to do. What is that problem you're trying to solve? What are the functional requirements necessary for your design? Okay, so that's the problem formulation stage. Once you really understand the problem and you really understand the functional requirements and how they relate to the customer requirements, you can start looking at concept design. And concept design is the part of the design process when alternative design concepts are generated and selected for further development. So let's talk about how you go about doing this, all right, and what a design concept is. So a design concept is the abstract embodiment of a physical principle, material, and geometry. And one important thing is that these design concepts should be developed independently. Okay, this is a major mistake that I see teams make occasionally is everybody will get together in a room and say, let's do a design concept. Let's come up with some ideas, right? And what invariably happens is you're all seeing what everybody else is doing. And as soon as that idea is put into somebody's head, then you can't get it out. I mean, you're already kind of geared towards assuming a certain kind of design. So you really want to develop these solutions independently at first, and then you're going to come together as a team and work through and combine different parts of different solutions to come up with an overall design idea. And as you're doing this, at this stage in the design process, you want to consider certain things. You want to think about, will you be able to manufacture whatever the concept is? Will the concept work in the desired operating location? Does it meet the marketing requirements? Does it meet minimum performance requirements, etc.? Okay, so common characteristics of design concepts, they work by some physical principle. Physical principles act on a surface or an object. You want to imply relative motion or surface types, and you want to imply general material types. So like, are you going to use an aluminum or a steel, or is it going to be wood or something? It probably shouldn't be wood. We don't typically use that in engineering systems. All right, so those kind of general things should be known. And so what I would suggest is you go about and you start creating design sketches. Okay, you do this independently, as I mentioned. So for each person on the team, you might come up with, let's say, 10 design sketches. And in those sketches, on each one, you'd want to identify what is the working geometry, what is the physical principle, what kind of material, what is the motion of the device, what are disadvantages, what are advantages, and what are constraints. And let me tell you that this is, if there is one part of the process that is the most important, quote unquote, I guess after really understanding the problem, after that, I'd say this is the most important part of the whole design process, because this is where your designs are going to succeed or failure, not when you're actually going to, machine the parts and put it together and stuff like that. And you can see that these design sketches are absolutely not, and I'm going to put a box around that, not just about drawing random lines on a piece of paper. I've seen this in the past where I've actually seen someone turn in a design sketches like this, where it was like create a Skittle sorting machine, and so they had a drawing like this, and it was like this with a hand. I'll just draw a gripper, but they like drew a hand, and that was their whole design sketch. This is not what you want. That's just, you're not really putting any thought or effort. When you draw these things on the page, you need to think about like physically building this machine. So you can see this is a design sketch for an autonomous walking robot. And you can see the early design sketch ended up corresponding to very close to what they actually ended up doing. And there are a lot of modifications from what was in this original idea, but these design sketches are absolutely critical. You got to take this part of the design process extremely seriously, because that is where the magic happens. That's what's going to separate the great teams from the teams that have a project that doesn't really work. And so what you do is, once everybody has these sketches, so you might have 40, 50, 60 different ideas. You want to go through and you can take these, and we have formal methods for how you can compare different design ideas. And so the one that we're going to talk about is something called the weighted rating method. So let me show you what that looks like. What you do is you come up with different criteria that are critical in your design. So maybe it needs to be highly efficient, highly reliable, low maintenance, low cost, and maybe we're going to compare a gear to a chain. Okay, those are two options, and you might have a bunch more. And what you do is you assign important weights, similarly to how we did with the sub-functions prior. So you might say efficiency is really critical, so that's 35%. High reliability is important, but not as important, so 15%, 25, and 25 should add up to 100. And then for each design, you can give it a rating. So you could say, okay, for the gear, this is really efficient, so we're going to give it a 4 out of 5, or 4 would be the highest. So this would be a very good rating. But maybe for the chain, it's not quite as good, so we'll give it a rating of 3. So it'd just be good. Or maybe it's completely unsatisfactory, so you would give it a 0. So you go through each of the different parts of that, and you kind of rate different designs. Now, you're not going to do this for all 50 of them. Maybe you select the top 5 to 10, whatever it may be, and you go through it and do that process. And once again, this is just to kind of get the discussion going. There's no right or wrong analysis here. All right. And a lot of times I suggest that people do these when you present these designs, if possible, do some of this with it independently, so you don't know actually who created the design. So that can always help as well. And so what you do is you say, okay, for the gear, you have a 35% weight. You take that times the rating, gives you a total value of 1.4. So you take 0.35 times 4 gives you 1.4. And you do that for each of the different criteria, and you get a total score. So the gear might have a score of 3.2, and the chain might have a score of 2.9 or something like that. And so that just gives you an idea of how people are rating the different design ideas. And then what you typically do is you go through this process and you can see, oh yeah, maybe we can incorporate some concepts from the gear and some concepts from the chain and some concepts from another idea and make an improved idea. All right. So if we were in class, which we're not, I'd have you guys go ahead and do this with your team and get this going and start the discussion. Um, just to at least figure out what are the criteria you're going to be looking for and what are the important weights. And then once you get the designs done, then you can go through and fill out the ratings and whatnot. But it's good to have some idea about what are the criteria for your concept design and how important are those different things. So you can think about that when you're doing your design. And as I mentioned, the concept design stage is critical. Teams that take this seriously do really, really well. Those that do not often struggle. Then we have the next phase of the design, which is the configuration design. So let's talk about what that is. So in this part of the design, you have a general idea of what your design is going to look like, but then you really want to start thinking about some other questions. What are the type of actuators you're going to use? So you might say, okay, you have linear motion. Does that mean you're going to use an electrical actuator? Is it going to be pneumatic, hydraulic? What kind of actuator are you going to use? How many of them are you going to use? Can you simplify the design process? How many links are you going to have? How many joints? Things like that. And there are different ways that different things we're going to design for. One, you want to design for function. All right, so that means you got to have the customer in mind. So are the parts strong enough? Are they too flexible? Will they buckle? Do they use too much energy? And so on and so forth. We also want to think about design for assembly. You want to try to minimize part count. You want to have a modular assembly. You want to use standard parts when possible and design parts with self-locating features, all these kinds of things. And then lastly, design for manufacturer. Is the manufacturing process costly? Their tolerance is too tight. Is the raw material available in standard form? You got to think about all these things in the configuration design. So it's sort of taking that concept to the next level in your design process. And we also have design for safety. Okay, this is always important in any design. What kind of safety measures do you have in place? Do you have an emergency stop or other way to shut down power? Are sharp corners removed, etc. So let's take a look at some examples here. So these are 4 different products that each had the same customer specification. So the customer specification was they had to design a robot that could follow a predetermined path. That's the black tape that you see. And it had to search for a dumbbell, and when it identified the dumbbell, it would pick it up. So they didn't know what the path was going to look like ahead of time. They didn't know where the dumbbell was going to be. They just know there was going to be some path that they had to follow and find this dumbbell. So it was meant to mimic like a robot that could, in a natural disaster, go and find a human and pick them up and bring them to safety or something like that. And so these are the results. And I want you to take a look at these 4 different designs and really think about what are the positives and negatives of each design, and what do you think motivated people that were actually doing these designs. And then we'll kind of talk through that. All right, so let's talk through each of these and which one was actually the best and which one was not, I don't want to say the worst, but the most challenging. All right, so the winner, I would say, is the one all the way on the right. And let me talk about what this team did that was so great. So you can see this team had a really simple walking robot that just had these 4 legs that would kind of pivot, and they could walk beautifully, follow the path. It was lightweight. They only had to machine, I think, I don't know, something like 8 parts or something like that, maybe even less. Maybe it was even 4 parts that they had to machine to build it. So they actually completed their project in February and were way ahead of all the other teams. Versus if you look at this first design, it looks really cool, right? And you can see why the students went with this design, because it looks like a Star Wars robot, it looks really neat. But was it actually going to do what they wanted? Well, kind of. It actually could walk. They came up with a really cool mechanism to make it walk, but they actually just spent hours and hours and hours in the machine shop because all of these pieces had to be machined, and it was crazy. The amount of electronics, everything was just over designed. And the reason that team chose what they chose in the concept stage was because they thought it looked cool and not because it would be practical. Okay, and so you have to try as much as you're going to want to choose the cool looking option. You need to think in a practical sense. What is going to work? That's what it comes down to. And the one on the right, that one was built to work. The one on the way on the left was built to look neat. And then you have the two in the middle. So the second one over also did a nice job walking, and that robot was built. They were motivated by building a smart robot, so they were able to map out an entire room, and they could walk in around any path without seeing any black tape at all. But it wasn't the smoothest walking. It was more designed around sensing and computational power. And then the other one, the blue one, was also very good. It was a pretty simple walking mechanism and did a nice job as well. But they didn't really need, let's say, 6 legs. They could have done the same thing with 4, which is what you see in the design at the end. So the reason that I show you these is always remember that whatever you're designing is going to become reality at some point. So you better make sure that it's practical and it's real. And then we also have what's called the parametric or detail design phase. All right, so let's talk about that. That is when you bring in the mathematical analysis to solve for specific design variables. So what you're going to want to do is come up with different design variables. Let's say the robot has to be designed to carry a certain amount of weight. Okay, and so your link lengths, for instance, in your mechanism might be a design variable. You get to choose those lengths and dimensions, and so how are you going to optimize your system? And that's where a lot of the mathematical analysis that you guys have been doing throughout your time at MSW really comes into play. You're going to apply what you've learned in your coursework to these real systems, which I think is going to be fantastic for you. All right, so here's an example of what I'm talking about. This is a whiteboard robot that could basically take inputs and write out any word on the whiteboard. So you have these 2 motors as inputs. And so one thing you might need to do is you might need to simulate a control system for this robot. Okay, so in doing that, you come up with your equations of motion, and you can get expressions for torque profiles. So this is how you're relating the mathematics that you do, let's say in a controls course, to your actual design. Right, and then you can go to Simulink and you can simulate, we can actually predict what that torque requirement on that motor is going to be before actually building the robot. So that's where you got to do all these different kind of analyses that we've talked about in your different courses. And this design process, let me just emphasize, is really iterative. Okay, so let me just go back. It's one thing I did skip over. This is something where you're going to have to iterate quite frequently. So it's not going to be just a straightforward path. You might have a concept design, and your team might decide, we're going with a 6-legged walking robot. And you might get a couple weeks in to that design, and someone says, wait a minute, what if we just use 4 legs? We could do it cheaper and faster and better. And then you say, oh yeah, that is better. Don't be afraid to scrap what you were doing and go back and start over, because making those changes now could save you tremendous amounts of time, energy, cost later on in the process. Anytime you have a design change late in the game, that is what you don't want. You don't want to be a week before you're going to have to present this thing, and someone says, this is not going to work. We need to redesign this whole subsystem. That's so much time and effort and expense. And that's why these early simulations, these early design talks are absolutely fundamental. You have to get that right, and that's going to really help you produce a great design. Okay, and so like I said, you're going to take what you have learned in your courses and relate that to your project, right? You're going to want to come up with different design variables, which are different things that can be calculated that you can optimize for your project, and you'll do that by using all the theory that you've been learning in your courses. And then finally, prototyping is always a good thing to do. And I'm not saying that you have to have, the most complicated prototype, but if there's something, where even though you've got a simulation, even though you can simulate on the computer, a lot of times a physical prototype will teach you things that you just wouldn't have predicted ahead of time. Okay, so if you can manage in a safe way to do some simple prototypes, you can really learn a lot and save yourself a lot of trouble when you go to actually have to build this thing by doing some prototypes. So you may want to just set a deadline for the first term. Let's say by the end of the quarter, you guys have different parts of the subsystem prototypes, or maybe you also start the programming of your system early. Maybe that's one area where a lot of times people in a mechanical engineering program maybe not as confident with programming motors or something, and you can get started on prototyping that kind of stuff and just learning those fundamentals early on in the term, so you're not just doing this all in a linear fashion, right? Remember, each person will have their technical area of competence, and you want to get started on that stuff right away. So I really hope that you enjoy senior design. I'm a little bit jealous because senior design is one of these times where it's really one of the few times for a lot of people in their careers where you get to design a system from the ground up. It's just not always the way it is. Even if you go work for a really innovative company like Tesla, you're still going to be doing part of the car. You're not designing the whole car from scratch. And so enjoy the process, enjoy senior year, and good luck, everyone. Thanks.
All right. Well, I hope we all enjoyed that. I think Brian's got a lot of great insights and can really help. I know we don't really have a lot of formal training on how to do design, so this is probably kind of the closest thing you're maybe going to get to sort of a formal guide on how to actually go through the process. So revisit that if you need to throughout the quarter to remind yourself kind of what step in the process you're at and where you might need to go. And to round things out, I'll just remind you that your problem statements, which is kind of step number 1 that he talked about, and that you'll need to hand in to me next Tuesday, are going to be really important for you guys to get right. So meet with your groups, meet with your advisors, get that problem statement nailed down, and we'll see you guys next Tuesday. Thanks.